All right, so today we're going to be looking at section 10.1, which is looking at relative maxima and minima, or some curve sketching. We're really not going to be doing a ton of curve sketching in this section. Primarily the reason why is because there's some other stuff in the future sections that we're going to be looking at that's just going to help us in our process of sketching curves. So you'll see. But I'm going to probably take quite a bit of time on this section purely because this is a really critical and crucial section. It really sets the stage for a lot of what we're doing down the road. And so that's what we're going to do. We're going to take some time on this, kind of talk through it, and then hopefully this will make sense as you start to work on the assignments. Okay. So one of the things that we can learn quite a bit about this content is how our original functions, derivatives, and higher order derivatives like second derivatives all tied together. A lot of it is really graphical. There's a lot of graphical connections that you can draw here, and so hopefully this section will illustrate some of that. Let's just think about, for example, something. This is going back to college algebra, but one of the things that we did in college algebra was if you had a quadratic equation, or a quadratic function, I should say. If you had a quadratic function, you could use a formula to determine the vertex, which was either a maximum or minimum point, okay? So the cool thing about that is we can actually utilize some calculus to figure out what the vertex is without actually having to utilize the vertex formula. So here are some concepts and some definitions that we're going to be looking at. F has a relative max at the value of x is equal to c if the function right here evaluated at c is bigger than or greater than f of x. In other words, if you think about like the surrounding areas, this c is like the peak. So it's at the top of the mountain, okay? The relative min, it's kind of the same idea. Everything else, the whole function is actually going to sit below. Actually, I flipped that. This should be f of c right here, so that's a little bit of a glitch on these notes. So FYI, you may want to correct that. If f of c is less than or equal to f of x. So again, the function evaluated at c is, what it's saying is that the point kind of sits below every other surrounding part of that function. So it's a local minimum. Using maxes and mins, which is what we call maxima and minima, it's just kind of the slang, we're going to be doing a lot of optimization. And so you'll be seeing that throughout a lot of what we do here in the next few sections primarily, but even as we continue through the course. Relative max min, you can see it just by looking at a graph. Again, we're going to be doing a little bit of this here. The global max or min exists if you it's like the biggest one on the entire function. Okay, so sometimes you can consider endpoints of a function. Sometimes it's just smaller things. Like in a parabola, it's just going to be wherever the peak is. So if it's a peak, it'd be, like a inverted parabola would be a maximum. A normal parabola that you see, it's got that traditional U shape to it. So that would be like you'd have a minimum at that bottom part. This is a really great graph, I think, that does a good job of just kind of illustrating some of those definitions. So for example, like this right here, like if I were to treat this x value, so suppose this is the x axis right here, okay? And I said this was like x equals c, it's just some x value. F of c is going to be the function evaluated at that. It's like the y value, okay? So that y value is the lowest of all the surrounding y values attached to it. That's all that this was saying up here, okay, for the minimum. So it's the smallest of all the ones surrounding it. Global max and min, it's a little different because it's the biggest on the entire function. So sometimes you may be asked to find those, and you'll just have to visually identify what those are. But you can see even there's some other kind of local minimums and a local max here as well, just as we go through. Now, the other global minimum in this case would just be at the very, very bottom. So again, the minimums and the maximums, they're actually tied to the y value, or the function evaluated at that particular x. It's not just like the x value is kind of like your input. Your output is whatever your y is, and that's the thing that we're interested in to determine whether or not something is a max or a min. It's whatever our output is. So if our output here is smaller than all the ones around it, it's a min. Up here, it's bigger than all the ones around it, so it's a max, so on and so forth. Okay? So, important thing to remember, how do we figure out where we can get minimums and maximums using derivatives? Well, if you think about a derivative, we've talked about this before, how the derivative can mean a couple of different things. It's velocity, or the instantaneous rate of change, or the slope of the tangent line. I'm going to focus on that last one here real quick, the slope of the tangent line. Okay, so if you were to take this graph that we have and draw corresponding tangent lines at every single point, what you'll notice is that the minimums and maximums, the slope, it's a perfectly horizontal line at the maximums and the minimums, or I guess the minimum and the max, whatever. It's a perfectly horizontal line. So in other words, the slope of that tangent line is actually 0. Now what's really good about that is that we can just take the derivative, and since the derivative represents the slope of the tangent line, we can set it equal to 0 and then find our values that we need for the x values. So that's really what this paragraph down here is saying. It's like we can take the derivative and see where the x values equal or correspond to where the derivative or the slope is equal to 0. And we'll do some examples of that, so hopefully it'll make sense. That brings us to a critical value. What is a critical value? I think in college algebra we briefly covered this, but it could be a couple of different places. So it's really where the derivative equals 0, the derivative of our function equals 0, or the derivative is undefined at a particular point. So if, for example, I had a rational function, right, and you have say like an x squared over x plus 3, okay? X equals minus 3 would be one of those critical values, and the reason why is because if I plugged minus 3 in, it would cause that denominator to become 0, which would make the function undefined. So it's a couple of different situations. It can happen in a few different places. The critical point is really just the corresponding point associated with the critical value. So we take the x value that we get with the critical value, and we sub it back into the original equation, not our derivative, our original equation, and then we'll get our critical point. Okay? So how does this all look graphically? Again, we're going to go through some examples, so if you're just like, man, this is information overload, I understand that 100%. If I were you, I would go back and take actual notes on this section, just listen to the video a few times, and then it'll start to kind of make sense. So let's take a look at this graph here, or these graphs. So here, this is our original function, okay? Our original function. Since the derivative represents the slope of the tangent line, you can think of the slopes coming off of each of these points all the way up until we get to this as being positive, okay? So the slope of the tangent line, when we have a maximum point, we know it's going to be 0. But as we transition and we move from the left to the right up to the max, the slopes are always positive. That's where this comes from. Over here, to the right of that maximum, the slopes are all negative. So what you see is a big transition from the slopes being positive to the slopes being negative, okay? I'm going to use Desmos too on this a little bit later to kind of illustrate how the first derivative and the original function are tied together, and hopefully that'll make a little bit more sense. But it's the same idea. Here the slope is negative, right? The slope of every single tangent line all the way up until we get to the minimum is going to be negative, and then it flips and then it's positive. Over here, this is kind of one of those unique situations where we do have a critical value, but the slope of the tangent line is 0, but it's positive everywhere. And so this is what we call a horizontal point of inflection. We'll talk a little bit about points of inflection in the next section, but we don't really have to worry too much about that right now. Same idea here. This is going to be negative everywhere, but there's the slope is 0 of that tangent line. All right, so this brings us to the first derivative test. So if the derivative changes from positive to negative, okay, we've got this situation here. We have a relative maximum. If the derivative changes from negative to positive, so from negative to positive, we have a min, relative minimum. If it doesn't change sign, so it's both, if it stays either negative or it stays positive, it's neither a relative max nor a relative min. It's what we call a horizontal point of inflection. I did not include that in this section purely because we're going to be talking about it a little bit more in the next section, okay? So that's really the notes here that we're going to look at. Now, okay, let's go ahead and take a quick peek at some problems, okay? So let me open up my whiteboard real quick. And it's loading. Give me just a minute. Here we go. Yep. Come on. There we go. Oh my gosh. I hope this isn't too laggy. Let's take a look at y is equal to 3x to the 5th minus 5x cubed plus 3. Okay. So what I'm going to do on this function, I'm actually going to graph it on Desmos so you can see specifically what it is that we're looking at here. Okay. Let's maximize this, and we'll go to Desmos. Oops. One moment. Got to plug my keyboard in, so quick intermission. There we go. All right. There we go. So let's go to Desmos. So let's go to the graphing calculator here. And what we're going to do is I'm just going to enter it in as y equals. Usually for Desmos, it's just good to put in y equals for your kind of input and output variables. So the x's and y's, whatever. You can actually choose other variables instead of x's for the dependent variable. Minus 5x to the 3 plus 3. Okay. So you get this kind of goofy looking function here. Okay. So ideally what we want to do is we want to figure out the maxes and mins, but obviously you can see just by clicking on them that they're just going to show up there. So I'm just going to pretend that that feature isn't enabled because it kind of ruins my massive surprise. What we're going to do now is I want to take the derivative of this and I'm going to enter it in as y equals again. So the derivative of this is going to be 15 x to the fourth minus 15x to the 2, okay? So I'm going to shut this first function off. This is our derivative down here, okay? It's a fourth degree polynomial. And the critical values of this are going to correspond specifically to this guy right here, this guy right here, and this guy right here. Wherever these cross the axis, okay? The critical values, or crossing or touching the axis, either one, it doesn't matter. Wherever these things are crossing or touching the axis, these are going to be the critical values of this function. Okay, so I'm just going to go ahead, again, just the x values, not the y values. The y should be 0 because we're setting it equal to 0, so obviously. So the x values are the only thing I'm concerned about. So let me go in here, and I just want to show you really quick. If I were to take the derivative and solve, I would have y prime is equal to 15x to the fourth minus 15x squared. And now I'd have to set it equal to 0 and then factor this stuff. So set it equal to 0 and factor. We're going to have a 15x squared pulled out. And then here we're going to be left with an x squared minus, what is it, 3? No, 1. Duh. Hello. Math. It's hard. Okay, so we've got this guy. So basically what it means is we've got this piece which we can factor. Let's just do this. Okay, we can actually set this equal. 15x squared is equal to 0. And then what we have is x minus 1 equals 0. These are the factors. X plus 1 equals 0. So if I were to go ahead and just factor that, I would get these as the results. So in this case, x is equal to 0. X is going to equal 1. And x is equal to a minus 1. Okay? These are all the values. Again, I did it algebraically, but you can solve by setting the derivative equal to 0 and finding all these corresponding x values. Okay? Now, let's go back to Desmos really quick, because what's really cool about this is those are the x values that we just found, right where they cross the axis, okay? So this is on the derivative function. One thing I want to point out to you is that this derivative right here, these derivatives, or this derivative function, represents the slope of the tangent line at any point. So let me say that again more clearly and very slowly. This derivative, the function 15x to the fourth minus 15x squared, represents the derivative or the slope of the tangent line of the original function at any given x value that I input. So what does that mean? Well, really quickly, you can see right here, this above the axis means that it's positive, so the slope is positive. Down below the axis, the slope is negative, okay? Again, because it's a negative, it represents the slope, which is negative here. So again, right here, the slope, because it sits below the axis, is negative. The slope, again, sitting below the axis is negative. And then you see it shift, it jumps up here to positive. So this is what I'm going to suggest is happening. Because this function represents the slope of the tangent line, the slope going from positive to negative at 1 means that what we have on the original function at x equals minus 1 is going to be a maximum, okay? So I'm actually just going to write that down. So I'm suggesting that this is going to be a max. I'm just looking at the derivatives. I'm not looking at the original function whatsoever, okay? There's a lot of information you can gather just by looking at these derivatives. For 1, it was the complete opposite, so this is going to be a min, okay? And then for this one, because the slope, you'll notice the slope didn't change right there. It's the same. It's negative to the left and negative to the right of that point. That means that this is going to be I'll call it a horizontal point of inflection, POI. All right, so let's go ahead and compare this now to our original. So notice what happens. At 1, we have a maximum. Right here, we have a horizontal point of inflection. And then down below, so that's trying to find the, I'm going to shut this off. This right here is going to be the minimum, the relative minimum in that location. Okay? So again, this, the blue represents the slope. And so the slope right here is positive, 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 0. That corresponds to where this derivative crosses the axis. It's the same x value, so there's the -1. And then if I look up here at the, there it is. So you can see -1, 0. This is the x value that corresponds with this x value up here. The only difference is that we have to take that x value, sub it into the original to find the corresponding y value, okay? The position, okay? So the blue represents the slope, the red represents the position, okay? I'm gonna do another one here in just a few minutes so you can see, but just really kind of understanding the connection between all of these is so essential. There's also a test that you can apply. They call it a sign test, but the way it works is this. If you take a look at, suppose you've got your x and your f prime of x. So this is your derivative and your x value. You're going to substitute in for x right where, put your critical values in here. So there's going to be -1, 0, and +1. I know the derivative because I found it down below. This is where these are all going to be 0 at each of those critical values. That's kind of the point of finding the critical values. And then what you can do is in between all of these points determine what the slope is. So if I substitute in, say, like a -2, say I pick a -2 here. If I do a -1/2 right here, and then a +1/2 here, and then say a +2 up there. Okay. If I sub in a -2 into this function, okay, I'm going to get a positive minus a positive. So this, in this case, let's just see what it would work out to be. You can actually sub it all in. You're going to ultimately see that this is going to produce positives, okay? Then what happens if we sub in a -1/2 into the derivative function? It's going to be negative. So the shift from positive to negative is going to correspond to a max. Down below over here, if I sub in a 1/2, I'm going to get a positive. So a minus to a positive is going to correspond to a minimum. And then right over here, oh, I'm sorry, you know what? This is not. This is supposed to be a, this is our horizontal point of inflection. So this is actually going to be a minus. So this is where it's like that. There we go. Sorry about that. And then this one's going to be a positive, so that's where the min is. Okay. So anyway, we'll do a few more of these, so hopefully you're like not completely lost yet. There's a lot. There's just a lot of information. I get that. So hopefully as we go through this a few times, this will start to kind of make a dent. All right. So let's go ahead and take a look at another question. Suppose I want to look at, let's see here. Let's do this one. So let's do y is equal to x to the 4th over 4 minus x to the 3rd over 3 minus 2. All right, so what we can do here is we can take the derivative. So let's do the derivative here. X to the 4th over 4. You can think of this, by the way, as the same thing as 1/4 x to the 4 minus 1/3 x to the 3 minus 2. Okay, and then obviously the 1/4 times the 1 or times the 4. This is going to produce a 1, and then we reduce the exponent by 1. and then this is going to become an x squared, and the 2 goes away. So on this question, the very first part is we have to find the derivative, so done. Now we have to find the critical values, okay? So the critical values are going to be where this thing equals 0. So I can go ahead and factor out an x squared, and I'm going to be left with an x minus 1 equals 0. So an x squared equals 0, and then I'm left with an x minus 1. I'm going to cancel out of this because it's slowing my computer down. X minus 1 equals 0. So here we're going to get x is equal to 0 as our critical value for this one, and then over on the right we're going to get x is equal to a positive 1. Okay? So here's our critical values. Now they're asking us to find the critical points. So the critical points correspond to the x values subbed into the original equation. Okay? So the corresponding y value for this x is going to be, when I sub in 0 into everything, I'm going to get a minus 2 here. That one's easy just because that's a 0, that's a 0, and then up here it's just the minus 2. And then for the next one, for the 1, it's a little bit trickier. We just have to sub a 1 into that, and what we're going to get is a y value that corresponds to, for the x, the x corresponding to the value of minus 25 over 12. Okay. Again, I'm not going through all the algebra here, but if you take the 1 and you sub it in, you're going to get 1/4 minus 1/3 minus 2, and that's going to equal minus 25 over 12. Okay. Common denominators, adding, subtracting, a whole bunch of stuff, you're going to get this. So the points are going to be the points 0, minus 2, and 1 minus 25/12. Okay? So these are the critical values. And these right here are the critical points. Critical points. All right. So now that we've got that, we have to find the intervals of x values where the function is increasing and where it's decreasing. Okay. So what we need to do is we need to determine the positions or the locations where it's increasing and decreasing. Okay, that'll hopefully tell us where the maxes and the mins are. So again, notation-wise, this is what I would suggest doing. When is f increasing and when is f decreasing, the function, the original function? It's going to be increasing when f, oh my gosh, this is so slow right now, x is greater than 0, and decreasing when f prime of x is less than 0, okay? So we're looking at the derivative, and we're trying to determine where it's less than 0 or greater than 0 for the decreasing and increasing respectively, okay? So you can use some test values, or you can just graph it. I would suggest just graphing it because it's usually a little bit easier. You can visualize it. So let's go ahead and do that. So the original function, okay? We'll look at the original function, and then we're going to get the exact same thing. I'm going to show you how to do it using the derivative. So the original function here is going to be y is equal to x to the 4th divided by, whoop, nope, don't want that. I want the divided by 4, okay? And then we're subtracting x to the 3 divided by 3, and then minus 2, okay? So that's our function. And you can see it kind of looks like a little parabola, but there's kind of this little thing down there. So interesting. All right, so the derivative is just going to be x to the 3 minus x squared. Is that what we said? Yeah, I think that's the case. All right, so take a look. Oh, interesting. Okay. So I'm going to draw some comparisons here between these two functions, okay? Remember, the color's a little backwards. I mean, I'm graphing it on white and you're seeing it in black, so it's kind of like weird. This like greenish color right here is the derivative, and this pinkish one is actually going to be the original function. It's like our position, okay? So we're looking for intervals where x is increasing or where the function is increasing and where it's decreasing. Okay, so let's just take a quick look at the original function. Let's ignore this, okay? You can see right here that it's trending downward. The slope is negative, 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 all the way down to that point right there, okay? It's still negative here. Negative, 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 and then it drops down and we get a minimum. And then from here, it's the slope. Again, the slope of the tangent line of this is positive, 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 all the way up, okay? So that's the original function. On the derivative, now what we're doing is we're not looking at the slope of the derivative. The derivative represents the slope, okay? So if it's below the axis, it means it's negative. And if it's above the axis, it means it's positive, okay? The critical values are listed right here at 1, 0, and 0, 0, okay? The critical values, I said that specifically. So x is equal to 1 and x is equal to 0. On the original function, okay, let me shut this one off. On the original function, the critical values correspond to 0 minus 2, which we just found, or the critical points, I should say. The critical points are 0 minus 2 and minus, so it's going to be 1 minus 25 over 12, which I reckon that's what that number equals, okay? These are the corresponding, so again, if you look at the x values, the 0 corresponds to that critical value. This one down here, 1 corresponds to where it crosses the axis right there, which is the 1. So again, same idea. Okay, there we go. So now you can see kind of how they're tied together. The 0 and the 0 tie together, the 1 and the 1 tie together, and now we just look at the green function here. And again, wherever it's below the axis is where it's negative. So the right here, it's decreasing, it's below the axis. So below axis. And then right here, it's just where it's above axis. This is the derivative function, okay? The position function is a little different. So that right there means that it's going to be negative all the way up until we get to this value here. This, not that guy, this guy right here, okay? So it's decreasing from negative infinity to 1, okay? And then it's going to be, it looks like it's increasing every single value above that, okay? So above that, it's above the axis, therefore you can kind of see where the minimum is right here. Everything to the right of this, the slope of everything is going to be positive of all those tangent lines. So that's where that is going to be increasing. So increasing from 1 to positive infinity, okay? The 0 is kind of an interesting one because it's like a false, I don't want to say it's a false critical point. It is a critical point. It's just a point of inflection there. It's not, the slope isn't changing from positive to negative or vice versa. It's just staying the same. So the function's still either increasing or decreasing. But anyway, this is kind of what we get. So again, being able to see the distinctions or the differences between these graphs is really, I think, key, because you'll be able to know what's going on when you kind of jump back and forth between them. All right. Let's go ahead and do... Oh, and this last part, I'm sorry. They were asking us to classify the critical points as relative maximum, minimum, or horizontal points of inflection. So in this case, horizontal point of inflection is going to live down here, right, where this derivative, it stays negative. You can see it stays under the axis, so therefore it's not shifting from negative to positive or positive to negative, so therefore it's just remaining negative. It's going to be a horizontal point of inflection. And then over here, when it crosses the axis, again, the critical points, where we set the derivative equal to 0, this one right here corresponds to, it looks like a relative minimum. And you can kind of see that on the original function here, on that pink one. This is the original position function. It's just a minimum. It kind of bottoms out. Or again, you can look at the slope and say, well, it's shifting from negative to positive, so therefore it's going down, and then it's going up, so therefore it has to be a minimum. Okay? So this is what we call the first derivative test. All right. Let's do another one because, again, I really want to be as illustrative as possible, show you as many examples as I can, just because it's really helpful just to physically to visualize it. So suppose I've got y is equal to 1/3 x to the 3, x cubed, plus x squared. And one thing, too, I would recommend is if you're watching this and you're just like, man, this is kind of confusing. Yeah, I mean, I get it. It really is. The first time you start looking at this stuff, it's just kind of mind-boggling because it feels like drinking from a fire hose. So what I would recommend doing, like I said before, is just watch this video a few times, and if you're still kind of like not getting it, there are so many resources available on YouTube. Just search for like first derivative test, oh gosh, what's the word I'm looking for? Curve sketching, calculus curve sketching, something like that. And you'll probably find some other videos, maybe with some additional examples. And I think that probably will help illustrate what it is that we're trying to accomplish here. All right, so let's look at this question, this next question here. It's asking us to find the relative max, min, horizontal points of inflection, and to sketch the graph. We're not really going to be doing too much curve sketching. The reality is, like, the reason why in the course, the reason why you need to do curve sketching, I'm using finger quotes here because you can use a graphing device, It's more related to, do you understand the underlying concepts between what the derivative represents, what your original function represents, how does the max and min tie in, all that kind of stuff, okay? So that's the reason why we talk about curve sketching. So let's find the derivative of this. And the derivative, you've been looking at it long enough now, so hopefully you know what this is. This should just be x squared plus 2x minus 24. Okay? To find the critical values, we set this equal to 0. X squared plus 2x minus 24. And then we solve. So this, though, we can factor. Sometimes it's just nice to actually have ones that factor because it just makes it a little bit easier. So it looks like it's going to be a plus 6 and a minus 4. Okay? And so when I set these equal to 0, then this means that this is going to equal x is equal to a minus 6. And over here, this is going to be x equal to a positive 4. Okay? All right, so that means these are the critical values. Now we need to find the critical points. So I'm going to take these and sub it back into my original. So I'm just going to do y evaluated at minus 6, okay, is equal to 1/3 times a minus 6. So again, these are the critical points. Plus a minus 6 squared minus 24 times a minus 6 plus 20. And I'm not going to bore you with all the adding, subtracting, multiplying, and dividing, but you're going to get a value of 128, okay? Now if I do the same thing of 4, right, 1/3 times 4 cubed plus 4 squared minus 24 times 4 plus 20. Again, I'm not going to bore you. This one's actually a little trickier. It's going to be minus 116 all over 3. So fun. So again, on the original function, the points that correspond to our critical values are going to be minus 6, 128, and positive 4, minus 116, 3, okay? All right, so these are the critical points. And now what I need to do is to figure out what's happening. I'm going to do this without any graphing right now, and then I'm going to show you the graph, and then we're going to look at it, okay? So same idea. I'm going to make a little t-chart. Let's do this. Let's make it longer. There. This is going to be my f prime of x. And then I'm going to slap the critical values in for my x here, and then I'm going to pick values that live on either side. So for example, if I choose a minus 7, I'll choose a 0 here because 0 is usually really easy to work with, and then we'll do 5, okay? And so what I need to do is I need to take these values and then sub them in to my derivative, which is back here, sub it into that, and I just am looking for whether it's positive or negative. I don't care about the values at all. I just want positive and negative. So if I sub a minus 7 into this, I'm going to get 49 minus 14 minus 24, which is actually positive, just barely. So this is a positive. Okay. If I sub 0 in to the y prime, I'm going to get 0 plus 0 minus 24, which is a minus. And if I sub in 5, I'm going to get 25 plus 10, which is 35, minus 24, so that's a positive. Okay? So notice what happens. The slope, the f prime, the derivative, again, remember, it represents the slope. This thing is switching from positive to negative. So this is going to correspond to a max, okay? And then over here, it's going from negative to positive. So it's going to correspond to a min, okay? So that means that the point minus 6, 128, this is a relative max. Relative max. And 4 minus 116 over 3, this is going to be a relative min. So again, the idea here is I'm just using kind of the properties of slope and seeing where there's a change happening to determine what specifically is going on at those critical points. Let's go ahead and graph it, and I'm going to show you precisely what we just did, okay? Kind of the more graphical way of doing it. So let's go ahead and do the original function, and then I'm going to do the derivative, just kind of like what we did on the previous question. So the original function was y is 1/3 x to the 1/3, or x to the 3, sorry, plus x to the 2 minus 24x. Oh boy, this is going to be, I'm going to have to zoom out on this one, plus 20. Okay. And yeah, we're for sure going to zoom out here. So it's very narrow. So I'm actually, I don't know if you know this, but you can actually go down here and then change the scaling a little bit. So if you want to just do this between, I know the critical points, so it's going to be, or the critical values are -6 and 4. So I'm just going to do this between -10 and 10. Okay. And then take a look. So there you go, right? It just makes it a little bit easier. You can do the same thing in a graphing calculator too, if you have one. That's why kind of working on the algebra is sometimes a little beneficial, because you can tell where those critical values are. Again, so look at the max and the min. The max, -6, 128. It's a relative max right there, which is exactly what we found doing it kind of graphically, or algebraically, I should say. And then this right here is going to correspond to the -116/3. This point right here. So how does this look when we compare it with the derivative? Okay, I'm going to shut this function off, and then I'm just going to graph the derivative. Okay, and then hopefully you'll be able to see and draw kind of comparisons between these two. So y is equal to what is it? X squared minus 2x, or sorry, plus 2x minus 24. Okay, so what we did is we determined where this function crossed the axis. That's where the critical values come from. So the -6 and the +4 right there. These are the critical values. Okay. Now again, this represents the slope of the tangent line. So it's positive. It's above the axis, all the way up into a -6, and then it's negative. So that means that the slope is increasing, and then it stops increasing. Now it's decreasing. Decreasing, all the way up until we get to this point. Decreasing, and then it switches from decreasing to increasing. So that's like the thing. The position on the derivative is the slope of the tangent line of my original function. I know it's kind of weird, like that mentality. So again, correspondingly, look, this slope increasing, all the way up to the maximum, which corresponds to this point right here. So this black line being above the axis means that this slope or this function is increasing. Below the axis on the derivative means that it then goes and switches to decreasing. And then when we get to the 0 right here, that's going to correspond to the minimum. Okay? Where then it starts increasing again. And again, because it flips from below the axis, the derivative flips from below the axis to above it, it's positive. Now, let me clear all this stuff off real quick. Clear. Oh, I said black. That's actually white. Again, it's backwards for me. I'm looking at a white version of it, not a black version. So, FYI, everything is inverted. All the colors are inverted. So, okay. Check this out. What do you think? This is like a little bit of a primer going into the next section, okay? I'll let you think about it, and we're going to cover it in the next section. This minimum of the derivative is right here. What do you think that x value corresponds to on the original function? And it's not going to show up here on Desmos, but it does correspond to something, this minimum, on the derivative. I'm going to leave it there. I'll let you think about it. and we'll cover it in the next section. That's all I have for today. Like I said, I know that this can be like a lot to really digest in one sitting, so take your time working on this section. I normally, in a normal, traditional class setting, would probably devote 2 class sessions to this topic because it really just takes time to kind of adjust the mentality. So take your time. Again, if you're still kind of a little lost, I would go and look at other YouTube videos. I would not just move on to the next section, okay? Because we're just going to keep ramping up the level of difficulty. You need to make sure that you're solid with how this works before you move on, okay? That's all I have. And like I said, if you have any questions, feel free to let me know.